In this screencast, we'll go through a step-by-step process of how to handle a mathematical model which A, requires linearization, and B, requires the analysis of something that is not a pure step function. So to show this, we'll go through the example shown on the screen, where we have a tank of two streams with different concentrations of sugar being mixed together to get a desired final concentration. They note the fact that when the system is at steady state, we have the values that are provided on the right. But we note the fact that we have a step increase in F1 based on an operator error, but fortunately, the fact that in this problem, we see that we have a step change which happens in F1 by 2 liters a minute. However, this only lasts for 5 minutes and then the system is restored back to its original steady state. So the question is asking to determine how the exiting concentration changes as a function of time using Laplace transforms. So to start with, we'll develop a mathematical model for this process. An important point to note here is the fact that changes in the inlet flow rate are automatically compensated by altering the outlet flow rate. So in other words, a total mass balance is conserved. So in other words, F will always equal F1 plus F2. But if we were to do a sugar balance here, what we would find is that the accumulation of sugar equals in minus out. There is no reaction term going on, and we don't have to worry about any thermal properties of the system. So coming in will be F1 times C1 plus F2 times C2. As a units check, F1 C1 has units of liters per minute multiplied by kilograms per liter. So therefore we have a mass. So that checks out. Coming out will be the flow rate F, which here we'll write as F1 plus F2 multiplied by our concentration C. The accumulation will be derivative of the mass of sugar present as a function of time. That will simply just be our volume multiplied by some sort of density, which in this case can be represented by concentration. So we can multiply V. Here we're going to multiply times C because since the tank is well mixed, the concentration exiting the tank is the same as the concentration inside the tank. So you have dVC dt. We can factor the V out. So now we want to do, for simplicity's sake, is put this into deviation variables as we put this into Laplace transforms. This is not a necessary step, but it makes some of our solution process a little easier. So here, the things that can vary are C and F1. Note, if we were doing this in terms of F, that would also vary, but in this case, we explicitly wrote F as F1 plus F2 to make it a little easier to solve. So our deviation variables will be C prime and F1 prime. Remember, the generic definition for a deviation variable is just the variable at a given time minus the steady state value. As we look at our final equation and we attempt to get it into the Laplace domain, although everything is first order, an important point to note here is the fact that F1 and C are both variables. So we multiply them together, that is no longer a linear term, and there is no Laplace transform for that. So therefore, that requires an overall linearization. Here we will use the equation to handle a differential equation that needs to be linearized, which is provided below. So here our two variables are C prime and F1 prime. So the left-hand side will just be V times dC prime dt. And that will equal, first, our derivative with respect to F1. The second term goes to 0. And the third term will be minus C. Put this in parentheses because we multiply everything by F prime. But note, with C1 minus C, we have to evaluate it at the steady state value. So therefore, C1 is a constant, so there's no bar necessary. But C is not. So we're going to have to put a bar there. And for the C term, we only have to look at the third term on the right-hand side. With the derivative of that will be F1 plus F2 multiplied by C prime. Once again, we evaluate at X bar, Y bar, or in case the steady states for C and F1. So we have to add a bar to F1. F2 is a constant, so we don't have to concern ourselves with it. Now we take the Laplace transform, and we end up with V C prime S equals C1 minus C bar multiplied by F1 prime minus F1 bar plus F2 multiplied by C prime. If we move the C prime terms over to the left-hand side, and after a little bit more rearrangements, we end up with our transfer function in standard form. So we end up with a generic first-order transfer function where this term is our gain, which has units of concentration, divided by flow rate. This is our value for the time constant, where tau has units of minutes. Next, we'll evaluate the value of the gain in the time constant. So we'll have to go back to the information we had at the beginning of the problem. So if we look at what we had at the top, we have the values for F1, F2, C1. However, we do not have the value for C bar. C bar can be obtained by using an entire mass balance at steady state. So to find C bar, we'll use the same balance we had before, except the left-hand side is 0. And that will leave us with 0 equals F1C1 plus F2C2 minus F1 plus F2 multiplied by C. So in other words, C will equal F1C1 plus F2C2 divided by F1 plus F2, which equals 6 kilograms per liter, which is our value for C bar. So now we can solve for the gain as 3 over 5. And then for tau, we can solve for V over F1 bar plus F2, and that will just be 2. So this means that our transfer function is C over F1 prime equals 3/5 divided by 2s plus 1. But the next thing we have to do is we have to evaluate F1 prime in the Laplace domain. So to do this, we have to recall what was going on with our flow rate. So what we see here is the fact that the operator flipped a switch and instantaneously increased the stream by 2 liters per minute. But then after 5 minutes, the original flow rates are restored. So if we were to put this in mathematical form, what that would be saying is that F1 prime equals 2 for times between 0 and 5, and that F1 prime equals 0 for all other times. If this were to be graphed, it would represent what's known as a rectangular pulse, with the time axis from 0 to 5, and this being F1 prime going from 0 to 2. So we'll use the definition of a Laplace transfer, which is the fact that the Laplace of a function is equal to the integral from 0 to infinity of the function in the time domain e to the negative st dt. So for our case here, that'll be the integral from 0 to 5 of 2 e to the negative st dt plus the integral from 5 to infinity of 0 e to the negative st dt. The second integral quickly goes to 0. And what we're left with for our Laplace is the integral will be negative 2 over s e to the negative st evaluated from 0 to 5. You can rewrite this as 2 over s multiplied by 1 minus e to the negative 5s. And this is what we'll substitute in for F1 prime. So when we substitute into F1 prime and rearrange, we can restate the concentration C prime as 3/5 over 2s plus 1 multiplied by 2 over s times 1 minus e to the negative 5s. What this represents is a first order response minus a Fock-T response. So there are tables in which you can evaluate it explicitly. C prime, our deviation variable here, will equal. So the first order response is of the form Km times 1 minus e to the negative t over tau. The Fock-T will be of the form Km multiplied by 1 minus e to the negative t over tau. But this t has to be replaced by the dead time, t minus t naught, and the second term is only valid when t is greater than t naught. So if we substitute all these things in, our gain here is 3/5. The magnitude of our step is 2. And then we have 1 minus e to the negative t over tau, which in this case is 2, minus the same 3/5 multiplied by 2, multiplied by 1 minus e to the negative t minus our dead time, which is t naught, 5 over 2. So what it means is the fact that our concentration will obey the first term only for when t is between 0 and 5, and that C prime will equal, and this is valid for all other times. If we plot the data based on the functions we provided, we'll get the graph shown below. If we look at this graph, it makes sense, because initially by increasing the flow rate of the more concentrated stream, our concentration will go up. Eventually, it will go back down and reach its old steady state once the switch has been flipped back, because we now regained the original flow rate, which would mean the fact that over time we would regain the initial steady state. Note the fact that we could also graph this as our y-axis as c without the deviation variable by starting from our steady state. So we go from 6 all the way up to 7.2. So here we showed how to solve a dynamic system by going through all the steps of developing the mathematical model, putting in deviation variables, linearizing, taking the Laplace transform, and then solving our Laplace transform. Here, we use knowledge about the fact that we had very common transfer functions, a first order process and a Foto-T to conduct our analysis. However, these answers could have easily been obtained by using partial fractions or the Heaviside method.